Hi guys,
Hi guys, how are you?
Mr. Kane here,
Mrs. G.
and this is the last unit of the year.
Unit 18 gas laws. And let's just do this thing.
Alright, there's only 8 videos, so we'll be good. Alright, so chemistry's a gas.
Oh.
Goals for the units. Describe the properties of a gas. Well, it's kind of a recap of what we did first semester.
Right.
Describe how the KMT, the Kinetic-Molecular Theory, and explain how it accounts for observed gas behaviors.
Yep, that's easy too.
That kind of goes along with properties. Convert between different pressure units.
Oh, gonna need a calculator.
State the gas laws.
Oop, gonna need my brain.
The gas laws.
Gas laws?
I just stated the gas laws.
Stated the gas laws?
So I've done it.
Okay.
All right. Calculate the relationship between any and all variables of any of the gas laws. So pressure, volume, temperature, and number of moles.
Yep. Okay.
Discuss and solve problems with the ideal gas law.
More calculator.
And stoichiometrically calculate a volume of a gas.
More calculator.
It appears that there's a lot of calculations in this unit. It's all algebra based.
Yep.
And it's actually not too hard. It's a nice way to end the year.
Good. Properties of gases. Now we did this in first semester when we discussed the properties of the different states of matter. These are gases. Uniformly fills their containers. They're compressible.
Okay, which is why I can have a propane cylinder underneath my grill.
Yep, and that's why older people have those little oxygen tanks that are the size of a Dewar flask.
Ooh, yeah. What size Dewar flask? They mix uniformly with other gases, resulting in homogeneous mixtures.
Right, so you can put two gases together and they'll mix uniformly.
Mm-hmm.
Relatively low exerts a pressure on its surroundings, which goes with the previous bullet point.
Yeah, about 14.7 pounds per square inch, right?
Yep.
All right, so properties of gases. One of the properties is that the distance between the particles is the greatest of all these states of matter. They're 10 times farther apart than liquids on average. That means that they're 1,000 times the volume, because if they're 10 times farther apart in the x direction, 10 times farther apart in the y direction, and 10 times farther apart in the z direction, that's 10 cubed,
Yep.
which is 1,000 times volume.
So 1,000 times larger than a volume of liquid.
Right. They're considered fluids when we talk about things. Fluids are things that flow.
Right.
Gases
they
flow.
Yep.
Right. And they tend to have low density.
Kinetic-Molecular Theory, KMT for short.
This was the second thing after properties of gases.
Correct.
Right? All right, so KMT, it's a model used to predict gas behaviors. And basically it states that all gas particles are in constant rapid random motion.
And they're elastic collisions, so they bounce.
Right, they bounce off each other, they don't stick. They're very far apart relative to their size, so we can see in that graphic there, it definitely looks like there's a lot of volume, a lot of empty space.
Right, a lot of empty space between the actual particles themselves.
And this explains why they're so fluid and why they're compressible.
And technically speaking, gas particles are supposed to move in a straight line, but there's too much junk in their way. Shelves, faucets, people, desks.
Other gas molecules.
Other gas particles,
Yeah.
Yep. So they kind of bounce off things and go in a very erratic path, a very erratic pathway. Pressure.
All right, so we're under a great deal of pressure from the air around us. It doesn't quite seem like it. It seems like the air should be light, but it actually extends pretty high above the Earth.
Correct.
And the pressure is defined in scientific terms as the force exerted by something per unit of area. In this case, atmospheric pressure is the force exerted by a gas per unit of area. So we get F over A.
Force over area. And
Right.
pressure is really proportional to the number of gas particles, right? Because isn't Colorado less gas particles? Mountain climbing and stuff like that?
They say the air is thinner up there, right?
Yeah.
So there's less gas particles above you.
Right.
So therefore, there's less gas particles pushing down on you.
Yeah, so sea level is more, mountaintops less. That's why you need oxygen masks when you climb a mountaintop.
All right, so as far as our Earth is concerned, if we're on sea level, then the gases extend up to 120 kilometers overhead.
Oh.
That's a lot more distance than I thought.
Yeah.
All these particles wind up getting pulled down, and they all wind up colliding with each other, and this creates the atmospheric pressure that we're feeling.
Okay.
Fun facts, the mass of the atmosphere has been calculated. It is 5.1361 times 10 to the 18th kilograms.
Whoosh, that's
Okay.
a lot.
So what that means is that if you start turning that into pressure, this is the total mass of the
Mass of it,
atmosphere,
yeah.
all of it. If you calculate it as pressure, it turns out to be about 14.7 pounds per square inch.
Okay.
So that means every square inch of your skin is getting pushed on by the atmosphere with 14.7 pounds worth of pressure.
That's a lot.
That's a heck of a lot,
For
yeah.
every square inch?
Every single square inch. And think about how many square inches are in your head.
Yeah, yeah.
So another way to put that is 10.2 tons per cubic meter. That's metric tons there.
Yeah.
That's why it's got two N's in it.
That's a lot of pressure.
That's a heck of a lot of pressure, yeah.
Measuring atmospheric pressure. Ooh, mercury barometers.
Yeah, so when they talk about on the news the barometer's falling, the barometer's rising,
Barometric reading.
they're talking about getting a barometric reading, which is, this is what this is, it's a barometer. And the mercury barometer measures atmospheric pressure. Basically, they use mercury because it's got a very small evaporation rate and it tends to be very dense.
Yeah, and if I remember right, from AP chemistry, a water barometer would be about 14 times larger than a mercury barometer.
Yeah, because of mercury's density, it can be smaller.
Yeah, you can fill more mercury into a smaller space than you can water.
It's a pretty simple device. Basically, you've got a little dish full of mercury here. You take a tube that has a vacuum in it, and it's closed up on the top here, but it's open on the bottom, and you stick this tube in here. Mm-hmm. The pressure of the atmosphere winds up pushing down on the mercury, which winds up pushing the mercury up into the tube a certain height. You measure this height, you measure it in millimeters, and you get a certain number of millimeters of mercury.
So it's literally so much millimeters of mercury is the barometric pressure.
Exactly.
Yeah.
On a nice calm day and on the ocean, you get 760 millimeters of mercury.
Okay.
Okay, that's exactly one atmosphere.
Kind of standard measurement.
That's the standard. Now, if a storm front's coming in, that means you're going to have a high pressure system coming in. That means that atmospheric pressure would be higher, so it would push down more. If it pushes down more, it pushes the mercury up more, which means that you'd have a higher mercury column.
And the reverse is true then too, yeah?
Right. Low pressure systems, when they come in, after a storm has gone away, is leaving, you get a low pressure system. That's less force pushing down here, and that means less force pushing the mercury up, so it actually comes down a little bit.
The mercury barometer is dropped. Ah, we're bleeding into a conversion, aren't we?
Yeah, we're getting to conversions here. So that's the way that we measure millimeters of mercury.
All right.
It turns out that there are other units of pressure.
Well, I recognize the 14.7 pounds per square inch. That's what I put in my bike tire when I have to put air in my tire.
Right, because in America here we like to use PSI.
Right.
Millimeters of mercury is loved by the people who do barometric pressures, by the weathermen. Atmospheres is loved by scientists because it's a standard. Like I said, 1 atmosphere is a cold day on the beach.
Yeah.
Right, a cold, calm day. Some other guy named Tor came up with another unit. Pascal did some work with pressure too, and he came up with his own pressure units.
Right.
But they turn out to be so small that they're difficult to use, so we tend to talk about kilopascals if we're going to use the units of pascals.
101,325 is small?
Well, those units are so that each individual pascal is a small.
Oh, I see what you're saying.
It's kind of like a micrometer.
Okay.
Would you measure things in micrometers?
No, that's a pain in the butt.
Yeah, it's okay.
One of them is Pascal, the SI unit, isn't it?
Yeah, Pascal's the SI unit.
SI unit. Yeah. But we're more familiar. We use atmospheres more than anything.
Right, and the point here is this: we need to be able to use them all. So notice these are all equal to each other.
Yep, they're all pressure units.
So if, for instance, Mrs. Goswish, throw me out a number here.
Oh, let's go with 8,762 millimeters of mercury.
All right, what do you want to convert that to?
Let's go change that to PSIs.
All right, PSI. If I want to convert that to PSI, it's going to be really simple. Millimeters of mercury has to go on the bottom. PSI has to go on the top. I'm just going to pick out the 2 units that I need. PSI is 14.7 according to the equality on the top of the page here, and millimeters of mercury is 760. So the math is 8,762 times 14.7 divided by 760.
You get 169 PSIs.
All right, with 3 sig figs, 169 PSIs. Now, just to show how easy this is to continue to use, I'm going to use the exact same thing, and I'm going to convert to, pascals, just for fun. So millimeters of mercury still has to go on the bottom because dimensional analysis says so. Pascals can go on top. 760. Pascals is 101.325. Give me a number here.
1.12 times 10 to the 6.
All right. So notice we just used the units that we need.
I get the feeling that 169 PSA would be quite crushing.
Yeah, it seems like that's probably the sort of pressure you get under the sea.
Definitely blow up a car tire, aren't they around 35?
Yeah, if you're using that on your car tire, you've exploded it.
Yep.
Yeah. There's only one more thing to talk about today.
For this video. All right, temperature conversions.
Yeah, temperature conversions. So it turns out that we don't use Celsius temperatures with the gas laws.
Right, because they're all gases, and Mr. Kelvin experimented with theoretically getting down to 0 Kelvin. Mm-hmm. Almost got there.
Right. Now, the whole point here is that we can't have negative temperatures.
Right.
Because if you have negative temperatures, the math for the gas laws turns out to have
Yeah,
negative
you can't
volumes,
have- yeah,
negative pressure. Those things don't make sense. So
You have to convert it.
we have to convert it to Kelvin. Kelvin is an absolute system where
Right.
everything's positive.
Right.
And nothing can go below 0
And you
Kelvin.
have to have your temperatures in Kelvin for every gas law you do.
Right.
Celsius will not work. That's the #1 mistake at all levels.
So every problem.
Every time.
Every time.
Yep.
If
every
I'm
time.
given Celsius, convert to Kelvin.
Right.
And it's as easy as adding 273.15.
Yep.
So if they told me I had 0 degrees Celsius, it would be
273.15 degrees. Oop, no degrees for Kelvin.
no
Kelvins.
degrees, just
Yep,
Kelvin, right?
Just Kelvin.
0 degrees Kelvin.
Yeah.
So if it's 100 degrees Celsius, then it would be
373.
0.15 Kelvin. All right. And if it were negative 100 degrees Celsius, then it would be
173.
173.15 Kelvin.
Yep.
All right. That
That's
seems
simple.
pretty straightforward.
Yep.